Okay, so welcome to Information Theory Lecture 28. I'm wondering, would anyone like to hear music at the beginning of these lectures? Because I feel like maybe we should, most of these things, there's like some sort of song.
Of your own composition? Or?
Sure, I would be happy to do that. So I do have enough of them that would serve the purpose. Maybe that's a good idea. Yeah, I'll think about that for, not for Wednesday, but maybe next Monday, especially since we won't even be here next Monday. Okay, so here we are. This is going to be, I think you will like this lecture. This is going to be the lecture, actually no, we're not there, we're here. We're at Algorithmic Randomness, Universal Probability, and Universal Compression, although we probably won't get to Universal Compression. Today is going to be perhaps one of the most philosophical of all of the lectures that we do, including the ones from last quarter. So let's try to open our brains a little bit, and minds in particular, and think about the potential philosophical implications of some of the things that we're going to be talking about, even though we're talking about things that are in some sense mathematical, but maybe aren't as well. What we're drawing from is still chapter 14 of the book. Could you raise your hands if you've read it? Okay, I need to start assigning more problem sets, obviously. There's no outstanding homework, but that maybe will change soon based on the feedback I just recently received from some of you. Office hours. Can I ask you, are people planning to come by office hours today? Raise your hand. You haven't been utilizing these amazing resources I've been providing you, because the reason why is there's an interesting talk today from 3:30 to 4:30.
I'm going to the talk.
You're going to the talk. Okay, so is anyone else going to the talk? So maybe we should, this is the Argobal talk?
There's some optimization thing.
Yes, that's the one. So, all right, so if people wouldn't mind, if people aren't going to come by office hours, I would like to go to that talk. But it's not, if you want to come by office hours, I won't go to the talk. So raise your hand if you would like office hours today. And again, if you have any questions on any of this material, and you can't reach me during office hours, again, I know I've said this, but there's plenty of opportunity, plenty of ways that you can reach me. This is a reminder of what is expected for the final presentations, but I do want to remind you, so next Monday is our first actual deadline, and then after that we're going to have a deadline every Monday for the rest of the quarter. This is about midway, so I really want to see significant work, or I'd like to see evidence of significant work on Monday's deadline. So it's due next Monday at 11:45 p.m. electronically. I'm going to work to get complete feedback to you by the Wednesday of the lecture, before the Wednesday, so you can actually ask me any questions in class about any of the feedback I've given to you. So if you want to get a perfect grade on Monday, because you're going to be graded for each one of these assignments, then please, you don't have to have absolutely found the paper, but you should at least have found, you should have read many different, or at least many different abstracts, and have some candidate papers. And you can, in some sense, think of this assignment as a cleverly researched email. Right? So these deadlines are really meant to force you to communicate to me about what you're going to be presenting. So there doesn't have to be super polished prose or anything. You can be addressing me by any name you wish, but it should be, like I said, there should be evidence of significant work. So you still have a week to do that. If you haven't started, I would start now. Literally, not this second, but literally during the talk at 3:30, not my talk. Okay, so let's do a review. So, of course, we talked about entropy as a measure of complexity, but the entropy is a measure of complexity is based entirely on the probabilities, and not so much, in fact not at all, on the contents of the strings that we're interested in compressing. And there are other notions of sort of complexity, like for example when we have these different strings, the repeated string 0, 1 repeated an infinite number of times, that string in some sense is very simple. It should be easy to describe. Whereas this other string, pi expanded out infinitely long, is in some sense, even though it has no easy pattern, it is still easy to describe because you can describe a formula or a procedure to generate that string utilizing the formula, which is brief for pi. So something is special about these strings, whereas I don't believe I have this slide in the next slide, but remember the string that came from a particular draw of an infinite sequence of fair coins. That string is not possible to describe other than by describing the exact pattern of zeros and ones of the string. So that string in some sense is complex. The notion of a halting program, P. So remember, P is we're going to use P as our notation for programs. And P halts if it runs for a while. It's a program if it runs and eventually stops. Otherwise, if it goes into an infinite loop or never finishes, it doesn't have to go into an infinite loop. It can just sort of never finish. For example, this program that we talked about down here, which basically tries to find the smallest natural number that is not the sum of n squares. That program, if it does something fairly simple, like for example a triangulation kind of argument where you sort of start with the smallest numbers and you keep growing the numbers until you get to a number which isn't expressible as the sum of n squares, that program would basically run forever if you gave it 4, where 4 is equal to n. And that's shown by Laplace. And so that would be an example of a non-infinite loop, non-halting program. Because in some sense, it's not really an infinite loop. It's not sort of getting stuck in a silly loop. It's just still trying to search for the answer. And it doesn't know that it will never actually find one because of, in some sense, the naivete of the program itself. So that's a non-halting program. And then we have the notion of string complexity. For example, we have the string for the 0, 1 repeated string, which is very short, printing pi, or printing just a random sequence, is long because the string itself needs to be part of the program. And we define the notion of a Turing machine and a universal computer, and all reasonable computing devices are sort of reducible with respect to each other in polynomial time. And so therefore, it's sufficient to sort of define this next concept, Kolmogorov complexity, with respect to U, which is our notion of a universal computer. And again, the Kolmogorov complexity is a measure of the complexity of the string, x, based on finding a program that generates it and finding, in fact, the shortest program that generates it on the one hand, and also that halts. So we can't, for example, have a program that generates the string and then sort of keeps searching or something. It's still going on. It has to sort of generate the string and then at some point stop. It doesn't have to halt immediately, but it does have to halt. And so here's our definition. Right? So therefore, we can sort of think of it as like an algorithmic description length, right? Using the laws in some sense, or the rules, or the sort of the properties of that which is expressed by this computing machine, U. X is the output of that. And then a couple of other definitions, just to remind ourselves. The conditional Kolmogorov complexity is the resulting complexity that you get if the program also has access to a string y, but it's not charged in terms of its length for y. So it gets to use y, but it doesn't pay anything. Like a simple example is if the conditional Kolmogorov complexity of x given x is going to be a constant because it can just read a symbol, write a symbol, read a symbol, write a symbol, and you're only charged for the length of the program to do the reading and the writing, but you're not charged for x. And so therefore any string has conditional self-Kolmogorov complexity of a constant. And similarly, if these were IID and independent, the conditional Kolmogorov complexity, y wouldn't help you. If y was statistically independent of x, using our notion of statistical independence, then in fact y wouldn't help you. The next notion is not conditioning on another string, but conditioning on the length of the string itself. So this is different than conditioning on x. We're only conditioning on the length of x. So the program gets to use the length. But otherwise, it still has to generate the string x. And so again, it's just a slightly different slightly different definition. And we have these various bounds. Well, first of all, the first bound is to say that all programs are, in some sense, additively constant equivalent. And remember, without loss of generality, we can switch U and A. Of course, there's constant changes, but the point is that they're all sort of the same up to a constant. So that basically means like if we take strings whose length goes to infinity, divide by n or something, that constant's going to go to 0 for any two pairs of computing devices. We also have this bound, which basically says that if we know the length and we can describe the string x knowing its length, all we need to do is sort of encode the length and maybe some additional constant stuff, and we get an upper bound on the Kolmogorov complexity. And where this is sort of this recursive, repeating, adding logs, encoding up a number. And that sort of raised this interesting issue of, well, we need log n bits to store it, but we need to know how long it takes to store log n bits, and we need log n bits for that, and so on and so forth, up until we get down to 0.
Can I ask a question about that?
Yeah.
So in like C programming, right, we terminate our strings with the null character.
Yeah.
And so that means that you can't have the null character in your string, because then it would take that as the termination.
Well, I mean, remember, all you know is the length, right? So basically, here's the lead. First of all, this is an upper bound. Okay, number one. So, and like I said, this may not be a great upper bound. What this says, it doesn't say anything about the null cover. It says, like, here's the shortest possible description of x using a program where it gets for free the length of x. Okay, it doesn't actually have x. And usually when one uses the null character in a C program, one is using that to terminate the exact string itself. Here what one has is instead the length. Right? For example, like, let's say the complexity to generate a particular random string. Like, let's say we take an IID random string, right? Knowing the length, right? So if you know the length of a particular random string, we still somehow need, we get to use this length as for free. And so it's going to be shorter if we use the length that we can say for I is equal to 1 to print the string without actually having to actually stick on an additional special symbol that indicates the end of the string.
Mm-hmm.
Then it would be if we get to just use that as a loop termination condition. Right? So if, in some sense, because the length is free, it's always going to, in this thing here, it's always going to use that as the description length. Now in practice, C strings with the null character just turns out to be a very, very sort of nice and efficient and simple way of representing strings. But many other languages don't do that because, for example, if you're doing string comparisons and you just want to know whether two strings are equal and you have these null length strings, it's much more efficient to first check their lengths, and if the lengths are different, then you're done. Right? You don't have to bother. And what if these strings are really, really long? It goes from a constant time, oftentimes it might be a constant time. It's only if the strings are the same length do you actually have to scan the string.
And well, like buffer overflow times and all this.
There's all sorts of other things. So the null character is sort of a nice, it's not a universally used construct
I
in
guess what I'm
programming.
thinking is, so here this formula on the slide says that the cost of having to encode the length is that log star term. So does that mean that the C style of putting a string with the null character has that same cost associated with it too? Like somehow that kind of makes sense.
Well, that would be. I mean, first of all, this is a bound, right? So we don't know, but this is a bound. This is a upper bound of the true Kolmogorov complexity. It's not like a tight bound necessarily. But then, secondly, I mean, in this particular case, when you have a null character, you're guaranteed that the null character is not part of the string. Whereas if it's truly a binary string, you have to do something tricky, right? Like, for example, the repeating thing, where we know it's part of the string if it's two repeating bits and it's only a 0, 1 that ends up indicating a pair of bits that are different that indicates the end of the string. But in the meantime, you've paid twice the length because every bit is doubled. So that's not a very efficient encoding potentially. And that was the way of the 2 log L thing was a way of encoding that, just the number, which is another way of doing it. This is a slightly more efficient way. But yeah, I think the thing to remember is that these are bounds and that the lengths are not charged in the length conditional Kolmogorov complexity case. Okay, so does that answer your question?
Yeah.
Okay, good. The next theorem is very, very important for today's lecture. It basically says that there aren't many simple long strings. Most long strings are complex. Few long strings are simple. And the reason why, you might get distracted by this 2 to the k, and you say, well, you've always learned that 2 to the k, that's exponential, it's growing in k, it's big, right? No, but it's not, because it's basically saying that the number of strings whose Kolmogorov complexity is less than k is at most 2 to the k, right? But that includes strings whose lengths are much, much longer than k, where, length n, the number of strings of length n is 2 to the n, and n could be bigger than k, and so there's 2 to the n minus k additional, in some sense, strings of length n that not length k. And so that's exponentially more strings of length n than there are strings of length k. And so what this is saying is that amongst all of these, this exponentially larger set in n, exponentially in n larger set, strings of length n, there's only a tiny sliver of them, 2 to the k of them, that have Kolmogorov, at most, 2 to the k of them that have complexity k or less. So if you see a long string, and I'm saying this for a reason, your belief might be, without actually seeing it, if someone gives you a long string, you might, unless you have some reason to believe otherwise, you might guess and place your bets on it being complex. On the other hand, maybe you wouldn't place it on complex, and that gets into something, like I said, some of the philosophical things we're going to be talking about, and actually which relate very much to fractal images. So these images look very, very complex, and there have been many, many studies over the past 40 years that have shown the incredible diverse collection of types of structures that can be generated fractally by very simple algorithms. And in fact, many people, argue, and in fact, it's fairly believable that nature has a very fractal structure. The fractal structure of nature, and there's the notion of a fractal dimension, and there can be, surfaces that are infinitely long that have a fractal. Like, how do you measure the length of a coastline? Because if you no matter where you look at it, you keep using smaller and smaller lines, and it keeps getting longer and longer when you measure the length of a coastline. And so that's related to the fractal dimension. And these things are describable using fairly simple algorithms, even though they're very, very complex in nature, like the coastline or any of these kinds of structure. In fact, any of these things on the bottom, these images are very fractal and can easily be simulated. Can you tell which ones are real and which ones are fractal on the bottom? Well, I won't give you the answer. But the point is, this is not a fractals class, but we're going to use fractals a little bit as an example. One of the things we're going to do a little bit more today, as we did last time, is comparing k, which is a string complexity, and h, the entropy. And we're going to, after we're done with Kolmogorov complexity, in some sense, we're going to have an exercise in mundanity in some sense, but by looking at the Lempel-Zev, even though Lempel-Zev normally is very, very sort of sophisticated and interesting, but we're interested in sort of notions of algorithmic complexity, and when we're talking about algorithmic complexity, we need to say, well, if we can compress algorithmically, does that somehow violate the entropy inequality, and the entropy lower bound of compression? And it turns out that it doesn't, even though we don't really have a notion of probability, but we want to sort of resolve this apparent dichotomy. And in doing so, we need to first of all define omega, which is this number I've been warning you about all last quarter and this quarter, which is defined as basically the sum over all halting programs of 2 to the negative length of the program, which we know to lie between 0 and 1. And we also know, and we know that by the Kraft's inequality, because these programs are prefix free. No halting program is a prefix of another halting program. Right.
That's not clear to me why it can't. I guess I'm thinking of programming languages or there's jumps and that kind of thing.
Well, think about 2 programs. One of it's halts, and one of it It's the same thing, but with some other stuff at the end. You know, so basically, if this program halts, and if that's the complete program, it's going to jump around and eventually halt, right? And it's never going to use the stuff beyond it because it halted. If it doesn't halt, you never know if it's going to jump over. All right. So then any program which uses that halting program as a prefix is going to be the same program. So so that basically it's the same. You know, you can have extra junk at the end, but it doesn't change the program length. So you know, all multiple programs are going to be finite length, and they're not prefixes of each other. So here's our sort of using the Kolmogorov complexity of a string as its description length theorem, where we do have a probability distribution, and it's basically saying that as a description length, the Kolmogorov complexity is just as good as Shannon's coding length. Namely, even though this should be a bizarre theorem. It's basically saying this guy that I just highlighted in yellow doesn't know anything about the probability of x. It just basically looks at the structure of x. And it's basically, this is the expected length, you know, the expected per symbol, because we're dividing by n here. So the expected per symbol length. Doesn't know anything about the probability, but as on average, as an expected, as a length of string L, which again we know to satisfy Kraft, it's no better or worse than the Shannon length, 1 over p, log of 1 over p. And the reason why is because, you know, it's upper bounded by the entropy. It's like lower bounded by the entropy here, and upper bounded by something that goes to the entropy as n gets big. So again, we're doing this asymptotically. Okay. Now the question, you know, we might want to ask, and this is where we're getting a little bit philosophical, is what is randomness in the first place? I mean, I usually like to think of randomness as basically, as I said, I think once or twice in this class, an acknowledgement of our inability to truly understand the structure of the universe and its processes. And we utilize and we deploy this notion of randomness, for which we do have a sort of a reasonable mathematical framework to work within, namely Kolmogorov, which also the same guy, Kolmogorov, and measure theory, probability and measure. So it's basically, randomness is sort of a tool, which we're not sure really exists or not. So it's just an acknowledgement of uncertainty, an acknowledgement and an exploitation, in some sense, even as of uncertainty. So we can also potentially define randomness by, you know, whether or not we think it truly exists. We presume that there exist certain probabilities which characterize the things that we see, the processes that we see. And while that's sort of a fairly utilitarian, when you actually go into sort of the understanding probability, there's, as many of you probably are aware, there's a big debate in the statistics and the probability literature between the frequentist interpretation of probability and the Bayesian interpretation of probability. And so it's not universally agreed upon, even once you actually do allow there to be probabilities, how they should be interpreted. Do they correspond to belief? Do they correspond to counting? Is there true probabilities? And what we do now, what we're doing here is we're in some sense throwing that whole debate away, I think. And we're sort of defining probabilities entirely differently based on randomness interpreted algorithmically. So, and that can be called algorithmic randomness. And something that's algorithmically random basically says x is algorithmically random if we can't find a short program to print x. Okay, so it's, you know, consistent with our definition of Kolmogorov complexity. So we can, however, relate, and as we saw a little bit before, we can relate this notion of algorithmic randomness with what we think to be our normal notion of randomness when there are probabilities, and you'll see that they're actually similar. And this also relates to something which I said before already today in today's lecture, and I'm saying again because it's so crucial for the arguments that are to follow, which is the notion that there are few simple sequences, right? So the number of simple sequences are few. There are not too many simple sequences, whereas the number of complicated sequences are many. There are many complicated sequences. And just by looking at the number of few number of simple sequences and the large number of complicated sequences there are, we can actually use that concept as a surrogate for the probabilities which we don't necessarily, or at least we're not necessarily given. So this is sort of what we're going to be doing. But before we get into a lot of that, let's look at Bernoulli sources a little bit with respect to random variables. And first of all, say, okay, we've got a sequence of n Bernoulli random variables, fair coin flips, okay? And we're saying, based on just the probabilities, what's the probability, according to the Bernoulli probabilities, of it being highly compressible? Okay. So highly compressible means what? Well, here it says, here's the Kolmogorov complexity, right? That's the shortest description length of that particular string. And highly compressible means it's less than n minus k. So obviously, if the Kolmogorov complexity was n, we'd say in some sense it's not compressible at all if it was IID. But when we do draw from independent IID random Bernoulli fair coin flip random variables, any one particular string is unlikely to be compressible, but there is some probability of like the all zero strings, and there's the probability of 0, 0, 1, 1, 0, 0, 1, 1. They all have equal probabilities, but what's the probability of it being compressible by an amount k? And what this theorem says is that it falls off exponentially with k. So if you want to compress it a lot, it becomes exponentially improbable to be able to compress it. So in other words, most strings are incompressible. So how do we prove this? So let's write the expression. And then we're summing over all strings whose complexity is upper bounded by n minus k and looking at its probability. The probability of every string is just 2 to the negative n, right? All strings have the same probability under this particular distribution, right? Independent IID. And so now we just count. It's the number of strings whose complexity is less than n minus k. But this quantity times 2 to the n minus k, 2 to the negative n, this quantity here, which I'm outlining in yellow, that we have a bound for, right? It's 2 to the, you want to remember? N minus k, right? So it's 2 to the n minus k times 2 to the negative n, and we just get 2 to the negative k. So it's very simply proved. So therefore, since this is true, this is the theorem we just proved, since this is true, as we increase k, as k gets big, which means that we can compress that particular string, that random string, or that string drawn randomly from a Bernoulli sequence, the probability of it being compressible goes down very quickly. Hence, most strings are not compressible. So if we multiply the probabilities by n, so we just hit, it's n times 2 to the negative k, that becomes the number of sequences of length k that can be compressed by k bits. And it decreases exponentially fast in k. It's just in terms of the number. There's another way of looking at it. So based on this idea, we can just define the notion of algorithmically random. So remember, there's no probabilities associated with this definition. It's just saying, well, it's algorithmically random if the Kolmogorov complexity has as a lower bound n minus cn, where cn is a sequence of numbers that goes to 0 as n goes to infinity. And I guess this definition really is based on a sequence of strings. You can think of it as a sequence of strings, or really it's a sequence of prefixes of some underlying string. So as the prefixes as the prefix gets longer and longer and longer, the compressibility from the complexity perspective goes to n, meaning we can't compress it at all. So any string that has this property is called algorithmically random. Does anyone have any questions about this definition?
So Cn goes to 0 means the amount that you're compressing in is getting less and less.
That's right. So as we take longer and longer prefixes of a given underlying string, which is infinite, it becomes less and less compressible because the description length goes to n. Like, for example, here's an example. If we did take a sequence, an infinite sequence of IID Bernoulli random variables, maybe it's still improbable, but relative to the length of an infinite string, maybe we got really, really lucky and the first 100 bits are all zeros. Okay? But that's just not going to last, right? That luck is going to run out. At some point, you're going to start getting ones, right? Because it's already exceedingly improbable to get a sequence of 100 zeros in a Bernoulli sequence of fair coin flips. But maybe you do. But eventually you stop. And so what this says is, well, the first sequence of 100 zeros, if you're extraordinarily lucky, but you know, you can compress that really easily, but then eventually you're not going to be able to compress it once n gets larger than a certain amount. You're going to start seeing the fact that it was really IID. And so that is a notion of algorithmically compressible. It's any string that has that property that eventually it's the case that you have to use n bits to describe it.
It seems like you could also do something where you fix the complexity at a constant and keep increasing the length of the string, and eventually you'll reach a point where there are no more strings, like every string greater than a certain length.
But that's not true, because there are, like pi. Pi is an infinite length string, and it's simple, and it's got a primitive complexity.
Every finite string greater than a certain length would not be able to be compressed anymore, because there'll be no Turing machines left that halt that.
Yeah, I don't know. I mean, again, every finite string greater than a certain length. I mean, you can always, again, take these very, very simply just to describe strings, like, I mean, print all zeros, or print 0, 1 repeatedly, and there's lots of those things.
Even then, like the print all zeros, you got to get to a certain length where you just can't, because you got to store the length somehow when you stop printing zeros.
Mm-hmm.
So you'll get to a point where you can't store that length.
Sorry, what is the? I'm not sure I understand
completely
the point.
So you have a program that's going to print all zeros.
What is the main quest? What is your quest in this point?
That finite strings greater than a certain length can't have some.
Must have complexity greater than a certain value.
Yeah.
I'm not sure. I don't think that's true. I think that basically, like, for example, you can take these very, very simple strings. I mean, unless you're saying that this value that you're cutting off the complexity at must be very, very small, because, you know, you can encode the length very, very efficiently, right? Usually, and if you're just talking about commutative complexity, I mean, yeah, there's going to be some point, but I mean, you're going to be able to get very, very long strings with very low complexity. There are not going to be a lot of them. But
I just say it's not like prime numbers where they get less and less dense but farther apart. I think eventually you're just going to hit 0 and there's going to be no more.
Yeah, if you make the threshold very, very small.
I think no matter
Sure.
what you make it, if you go out far enough, anyway, it doesn't.
I think you're right, but I think that growth function is very slow. The point is that, sure, you're bounded by this length thing, just storing the length, right? Finite strings greater than a certain length. You know, if you set the complexity less than that length, then yeah, you know, less than the most efficient representation of that length. Yes, but I mean that's a very slow growing function. Representing the length of the string is not a big deal, usually. But what we do have is this theorem, another sort of notion that so we have the notion of algorithmically random. If it's lower bound in this way, we say that it's algorithmically incompressible if the ratio of the complexity, of the length condition complexity to n, so we're not even charging for the length, goes to 1, as n goes to infinity. So in other words, basically this says that it's incompressible if we don't pay attention to the length, you know, to storing the actual length of the string, which again is sort of something that doesn't cost that much. We have to use n bits, or we have to have something that's length n plus some constant. So it essentially means that we need to store the string. That's what it means. That's the only way to compress it, is just to store the string. And another thing to remember is that the incompressibility of a random string is such that if it has approximately, or exactly, or asymptotically exactly half zeros and half ones, the probability is close to or exactly equal to 1/2, which basically gives us an entropy of 1. So the question is there an analogous notion for cohomograph complexity? And it turns out that there is. This is in some sense a strong law of incompressibility. It's saying that if we have this infinite string and it's incompressible, then this limit, summing up the number of ones in the first n bits of the string divided by n, we take the limit of that goes to 1/2. So that is a necessary property of any incompressible, algorithmically incompressible string. So just like entropy, which says that we have a probability of 1/2 for any string which is incompressible, when there are probabilities. Here we're not saying that there are probabilities, but it's still sort of a frequentist way of saying, well, the ratio, the frequency of ones has to be about 50%, or exactly 50% asymptotically. So I already said this. So, again, there's nothing probabilistic here. We're just sort of counting. So how do we prove this? So let's say that theta n is the fraction of ones. And then we use from theorem 28.2.3. This is the theorem that gave us this. It was the theorem that lower bounded the per symbol expected cohomograph complexity, lower bounded by the entropy, and upper bounded it by the entropy plus this alphabet size plus something else and constant. So here in fact is it. So basically, we have this lower bound from algorithmically incompressible. We have this upper bound from this theorem. Okay. And Cn is something that goes to 0, right? We said that that's true. That's from the definition. And so therefore we have this property, right? We can say, so now we can sort of use the entropy. We can say, let's solve for the entropy in this series of inequalities. And what that gives us is a lower bound on the entropy. The entropy is lower bound by 1 minus this stuff on the right. Right. Well, let's expand. Let's look at that stuff on the right for a minute on the next slide. So there it is. It turns out that that stuff on the right goes to 0. Why? Because log n over n and Cn over n and C prime over n goes to 0. So that basically gives us this lower bound. And the entropy, which is upper bounded by 1, the lower bound is going to go to 1. So therefore, the probability or the ratio of ones to the length of the string has to go to 1/2. So interestingly enough, we're using entropy to prove a theorem about cohomograph complexity without there actually being any presupposition about the existence of probabilities. And the only reason why we're doing this is because we're doing this sort of counting to get a number that lies between 0 and 1. So it's not really circular reasoning. It's not, just in case you're worried, this isn't a circular argument. We're just counting and then sticking it inside of the entropy quantity and using the entropy quantity mathematically. Which, in some sense, is the basis of all of these combinatorial bounds that we have seen so far. For example, like the entropic bound of n choose k. Remember that. We have an upper bound of the combinatorial counting quantities and the multinomial and the binomial in terms of the entropy. And so this is an instance of that. And there are generally, in combinatorics, there's a branch of combinatorics called the probabilistic method, which I believe is pioneered by Paul Ehrlich, actually. But that basically corresponds to constructing probabilities and taking expected values and using the properties of probability and expected values without actually necessarily being probabilities truly, or without actually requiring one to have any sort of beliefs about or sort of assumptions about probability. We're just sort of using the mathematical properties of it to prove certain theorems. Okay, so the other thing that's interesting about this is that any such algorithmically incompressible string, for all intents and purposes, look random. So if we were, for example, to look for statistical regularity in any algorithmically incompressible string, we wouldn't find any. And like the reason why is because as soon as we were to find, if we had this infinite sequence, as soon as we were able to find any particular statistical regularity that wasn't purely random, we'd be able to exploit it. Like for example, in this one, let's say that we find that two pairs of bits, two successive pairs of bits tend to be more likely to be 1, 1 than 0, 0 or something. Then suddenly we can use that to compress the string to below 1 bit per symbol. We just group them into do things. For the ones that have 1, 1s, we'd use fewer bits on average, and this one you use more bits, and that one would occur with more probability. As soon as there's unequal probabilities, we would divide these strings into these blocks, or I should say partition these strings into these blocks, and if the probabilities don't correspond to a uniform distribution, we would then the more probable ones we'd use fewer bits and thereby obtain compressibility. But that can't happen, right? Then it wouldn't be algorithmically random. Okay, so now let's look a little bit more at the relationship between. It's another theorem associating cohomological complexity and entropy, and here's another sequence of Bernoulli random variables, and it's saying now what does this mean? So again, this is a random sequence. So that means that the cohomological complexity is a random variable, so a function of a random sequence. And so therefore, it's the expected cohomological complexity of the string, which is drawn from this length-n sequence of Bernoulli random variables. Then divided by n, so it becomes per symbol. And what this is saying is that it goes to the entropy, where the entropy is the probability that the sequence was drawn based on. And so to actually make this more formal, what this really means is that the probability of the per symbol cohomological complexity deviating from the entropy by more than epsilon goes to 0 for all epsilon greater than 0. So again, this is interesting because the probability in this case comes, but we're using the probability in this case comes from the Bernoulli random variable. So let's show two things to prove it. We're going to first show that the probability of k exceeding n times the entropy plus epsilon goes to 0. And then secondly, we're going to show that k being less than n times the entropy minus c goes to 0. Where c is another sort of epsilon-like variable. It's just another variable that we're going to be able to make as small as we want. The reason why we're using c and not epsilon is because we also want to use epsilon and c in the proof of part B. So let's first prove part A, which is this part, that the cohomological complexity can't exceed n times the entropy. So let's first define x bar of n, which is the ratio, is the counting the number, the relative number of ones in the length n sequence, the probability of ones in that sequence. And again, from that theorem, 28.2.3, we have this upper bound here, which just allows us to solve for this lower bound on the entropy, where again the entropy is of x bar. Okay. So x bar here. So where this is the same, this is basically this thing or this thing here. Okay. It's that probability. So then what we get is the following, that we know that from the weak law of large numbers that x bar approaches its mean, right? So theta is the mean. It's the mean of the random variable. The weak law of large numbers says that for any epsilon greater than 0, the probability of x bar deviating from the true mean by more than epsilon goes to 0. So that is something that we're going to use. And so that basically implies that these functions of these random variables also, these functions of these probabilities also go to the same value because of the monotonicity of the entropy within that range. And that's equivalent to this statement, which is just taking out the absolute value. So it's just being more explicit. And now let's plug in the quantities and the bounds that we know. So on the right-hand side here, we have epsilon minus entropy, epsilon plus entropy, and epsilon plus entropy. On the left-hand side, we have this, we have this guy here, which is the lower bound. Remember, that was the lower bound from the entropy that we saw before. So then when we solve for this, we get k over n minus the entropy is greater than epsilon prime, where epsilon prime is any number that can be made as small as we want. And then when we solve for k, we get exactly the quantity that we're interested in showing. So in other words, the Kolmogorov complexity will not exceed, with high probability, the entropy, the per symbol Kolmogorov complexity, which is the first part of the theorem. The next part of the theorem, we need to show that it's, in some sense, tight. And so again, C is going to be a representation. It's going to be another variable that we're going to be using as an epsilon-like variable. And so for any epsilon and C greater than 0, this quantity, which is the thing we want to show, is equal to summing over all strings whose complexity is upper bounded in this way. And then it's just the probability of that string. And now we're going to use typical set theory. Typical set theory lives. So let's break it apart into the typical sequences and the atypical sequences, because after all, these are Bernoulli random variables, right? So we can break it into two terms based on, it's exactly the same form, except that we're considering the typical ones and then atypical ones. The first term is the atypical ones, which we know to be upper bounded by the probability of the atypical set. And we know that to be no more than epsilon. And the right-hand side is the typical set, which is this guy. But since it's typical, we have an upper bound on its probability. Remember this guy? This is the 2 to the negative n h of theta, where theta is the true probability minus epsilon. Now we can count. We have a count of the typical set, which is yet another upper bound. Here's the count. So this is back up a minute to make sure this is clear to everybody. So we're basically moving this yellow bit out of the sum, and then we're counting the number of terms in the sum. And we can make this to be equal to 2 to the negative n, 2 to the nh minus c. And so what we end up getting is epsilon plus e to the negative n c minus epsilon. And that can be made, again, as small as we want. So the idea is, again, we first choose, we choose a c. To make this work, we choose any c we want, because the c is the thing we're trying. And then we need to choose an epsilon within this range. And for large enough n, we can get that epsilon to be, we can get that epsilon for any c. So again, it's an asymptotic thing. Okay. So that's the rest of that. That's the mechanics. The next section, the universal probability, is where we'll start getting somewhat philosophical. Now that we've got these mechanical tools under our belt, so let's maybe take a short break. This is a good time for a break, and we'll come back to the philosophy. Okay, so the next topic we're going to talk about is universal probability, and the whole idea of that it's possible to define probability in a very interesting and perhaps deep way using Kolmogorov complexity. So let's start by looking at entropy. So if the entropy is equal to 1, so the number of typical sequences of length n is going to be 2 to the nh, which is equal to 2 to the n. So all sequences are equally likely, all sequences are typical. Right? So what does that mean? That means that this sequence, so we've got a length n sequence, ID random sequence, which is the only way that we could actually achieve an entropy, a per symbol entropy of 1, right? Is is the following, that the sequence of all zeros, and n could be very large, it could be 1,000 or 1,000,000. The sequence of all zeros is going to have probability to the 1 over 2 to the L, where L is the length of the string. On the other hand, this string, which is, let's say approximately the same number of zeros and the same number of ones, and maybe just a fairly arbitrary random placement of the zeros and ones scattered about in the string, has exactly the same probability. Right? So these two strings, the string of all zeros and this arbitrary pattern of zeros and ones, has exactly the same probability. They're considered equally likely. But which one, let me ask you, which one is more surprising? Like, what one would you expect to see?
Random.
On one hand, you think, yes, I'd expect to see this patterns of zeros and ones kind of arbitrarily thing. I mean, if you flip a coin even 10 times, you're probably going to, do I have a coin? I don't know, does anyone have a coin? I mean, you don't need me to do it, but basically it's very likely that we're going to see the zeros and ones. And if we were to see all zeros, we won the lottery, right? This is amazing, this is surprising. But on the other hand, the string of all zeros it's got the same probability as the string of ones and zeros. So why is that? Is that right? I mean, is that something that should be the case? I mean, the one that's so incredibly surprising and so incredibly improbable has exactly the same probability as this typical one, in some sense typical. But on the other hand, using our notion of typical set theory, they're all typical. And in fact, they're equally all surprising. I mean, in fact, if we see any sequence of ones and zeros, we should be just as surprised by that one and amazed by that one as we are of the sequence of all zeros. Right? There's really no difference from a probabilistic perspective. On the other hand, which one is more simple? Which one's simpler to describe? The all zero ones is very simple to describe. All zeros. This other one, I'm even right now having trouble finding the words to describe it. The sequence of approximately 50% zeros and ones, or the sequence of an arbitrary placement of ones and zeros, or that thing over there. There's all these different ways of describing it, none of which really describe that string. In fact, on paper, I'm just describing it conceptually by using the ... notation. So obviously, the sequence of all zeros is easier to describe. The sequence of all zeros could be, in some sense, seen as simple, as more simple. Yet at the same time, it has the same probability. So the question then is Shannon's theory lacking? Is there some probable with the Shannon notion of entropy? It gives complexity to an ensemble of messages, and it gives complexity based on that ensemble of messages based on the probability of those different messages, not based on the content of those messages. And so on the one hand, it seems like there's a real problem with Shannon's theory, but on the other hand, we proved in this mechanics that we did last section that when there is true randomness, the Kolmogorov complexity and the Shannon length is about the same in terms of the per symbol coding length on average. So what's going on? What's actually happening? So Shannon's approach, first of all, doesn't ask how complex is the message itself. It just says it judges complexity based on the probability, irrespective of the complexity of the string. Okay. So how then, we saw also that we can use the Kolmogorov complexity as a coding length, even though it doesn't use probability. So what we want to do is we want to then come up with a coding length based on this sort of algorithmic complexity notion. And it turns out that this notion is actually very similar to Occam's razor, which probably most of you have heard about. Have you heard about Occam's razor before? So Occam's razor is a sort of a very important principle that's basically universal in nature, not just in, say, machine learning and statistics. So Occam's razor can be stated in the following fashion. So if there are multiple explanations of a phenomenon, then without any additional information, without any prior assumptions or additional knowledge that's interjected into and say influences us in other ways to prefer the more complex case, without any of that stuff, we would prefer the simpler explanation. Simpler explanations are more probable a priori. So what does simple mean? I mean, simple means basically it's easy to describe. And easy to describe means it has a short description length. Print all zeros. Print n zeros. It's very easy to describe. It's simple. If I were to come up with an explanation for why, for the string of all zeros, if I were to write down a sequence of 1,000 zeros, you would probably become very frustrated, right? Because you say, why are you wasting our time coming up with this very complex description of the all zero sequence? You would prefer a simpler one. You would be basically saying, I like Occam's razor's notion. So it basically says that short explanations or short causes of objects are the more probable ones a priori. So now suddenly we can talk about maybe probabilities. This is a prior on objects. Prior on objects should be ones that have a simple description. In some sense, this is really a prior probability on nature itself. We can say that nature in general could potentially be described by there being a prior on the objects and the instances of things, and the phenomena and the processes that we see in nature that has high probability on those things that have simple explanations and low probability on those things that have complex explanations. And so let's go back in time and look at Laplace's essay on probability, philosophical essay on probabilities from 1819. And this is something that Laplace wrote. So basically, he said as follows. This is a quote, actually, although he didn't write in English, of course. We arrange in our thought all possible events in various classes, and we regard as extraordinary those classes which include a very small number. So the ones, he's basically saying that those things that are strange aren't very frequent, so there aren't a lot of them. For example, then he says, in the game of heads and tails, if heads comes up 100 times in a row, then this appears to us extraordinary because the almost infinite number of combinations that can arise in 100 throws are divided into two cases. Case 1, in regular sequences, or those in which we observe a rule that is easy to grasp, or irregular sequences, and that are incomparably more numerous. Okay, so this is basically Kolmogorov complexity, right? This is in some sense saying that the description length is kind of like the thing that allows us to give us the complexity or the surprise of a particular object. Now this was written 150 years before Kolmogorov was formulated. I mean, this was before there were computers, or the notion of computing devices existed. But then the question is, how do we define regular? This is really what didn't exist. So somehow Laplace in his mind had this notion of what regular is. And what Kolmogorov did is say, okay, regular is basically, there's a program that generates that thing, a short program that generates that thing. So when we look around the world, whether we look at classrooms or people or plants or galaxies or buildings or pretty much anything that exists in nature, most things are regular. It's very rare that we actually see completely, apparently random dot patterns. The nature has a structure, and a very, very statistically regular structure. So what do we mean by regular events? So here, again, let's look back to the same essay. And he claims in 1819 that the regular combinations occur more rarely only because they are less numerous. If we seek a cause wherever we perceive symmetry, where symmetry is our notion of regularity. Symmetry is itself a complicated concept. If we seek a cause whenever we perceive symmetry, it is not that we regard the symmetrical event as less possible than the others, but since this event ought to be the effect of either a regular cause, or in modern parlance, a short program, or that of chance, the regular cause, the first of these suppositions, is more probable than the second. And that is the assumption. That is the reasonable assumption. So when you look at around the world, it just makes more sense. It seems more reasonable to assume that there is some underlying regular cause for the universe that we see. And then his example was a little bit less extravagant than the kinds of things I'm saying about, but basically he says, on a table we see the letters arranged in this order, Constantinople, and we judge that this arrangement is not the result of chance, not because it is less possible than others, For if this word were not employed in any language, we would not suspect it came from any particular cause, but this word being in use among us, it is comparably more probable in some person, or namely a program, has thus arranged the aforesaid letters, than that this arrangement is due to chance. So is that not essentially homograph complexity? I mean, except without the notion of there being a program or computer. So we have regular sequences, sequence of 4 zeros followed by 4 ones followed by 4 zeros. This is probably not going to happen by chance. It's very something is happening here. There's probably some cause that's causing it, according to this idea. This sequence. This is obviously the sequence of prime numbers. If we were to see this, it's probably not likely to happen by chance. In the movie Contact with Jodie Foster, she detected, I think this is right, I don't remember that movie that well, but when they detected in the movie a sequence of primes, that was basically evidence that there is life in the universe, besides on planet Earth. If you were to suddenly receive a signal from space and it was the sequence of primes, we would say, okay, well, this is probably not by chance. There must be some cause. There must be some underlying reason why this is happening. What about this sequence? Sometimes it's very hard to see. It's very hard to discern. This sequence looks like it might be random. Right? But in fact, it's very, very regular. It turns out it's just the prime mod I, the sequence. So if we saw this sequence, we might think, oh, look, it's random. It might even pass random tests. But it's a very, very simple program. Imagine slightly more elaborate programs. Imagine like a 1,000-line C program to generate this sequence. Or a random number generator, a pseudo-random number generator. It produces apparently random number generators. In some sense, we're trying to find short, finite-length programs which produce sequences which appear and pass all random tests. So that, in some sense, is exactly trying to find the limit of homograph complexity. We might be being simultaneously bombarded by enormous numbers of very, very regular sequences and signals that we just don't perceive or we don't see to be such because we just don't know the program that generated it in the universe. So the structure, apparent lack of structure, that when we look up, if there is any lack of structure, or what we don't see a structure, it just might be our inability to know what program generated it. I mean, a pulsar is another example. I mean, so this is just a quote from Wikipedia. So originally a pulsar was an entirely novel kind of star that came to light on August 6th last year and was referred to astronomers as little green men. This is written in 1968. Now it is thought to be a novel type of white dwarf and neutron star. The name pulsar is likely to be given to it. So, it's a simpler explanation. If the physicists can come up with some phenomena that explains this regular pulsing as opposed to little green men sending us binary regular signals, we prefer the simpler explanation. It's more likely.
So I went to Las Vegas once and they had above the roulette tables like a computer screen with a histogram of the last 500 wherever the ball landed, and then people look at that and then make up their explanations for their betting strategy.
Mm-hmm.
So maybe this philosophy can also betray us if we, so there are many things in life where the shorter explanation is more reasonable, and then there are other times it seems like for things that don't have a short explanation and we'll come up with one because we prefer it.
Well, in that particular case, I mean, it's more just a lack of information that they're giving you. I mean, in general, in gambling, the biases are against you. And that's not what the histogram shows you. The histogram is just showing you noise, really. And it's basically not doing anything to affect the probability that the house is going to win, on average. It's just giving you some assurance that what it's telling you is something that's statistically meaningful, but in fact it's statistically not meaningful. It doesn't affect the bias.
I know that, right? And we all know that because we study statistics. But if you're going for something simple, you might, or is that not simple to look at and say, oh, well, there are a lot of threes, so now it's not going to be.
Yeah, I would say that that's not that's an invalid explanation, because that's basically making assumptions based on incorrect information. I mean, you don't know if you have the correct signal, for example. I mean, if you have a limited history of the past number of plays, you're not aware of that, you don't realize that. I mean, here we're assuming that we have a complete explanation of the phenomenon, right, without noise. And we don't know. I mean, what is science? I mean, one of these things, I mean, you've probably heard that Bill Nye recently debated a creationist. I mean, the whole notion of science is oftentimes in the popular media portrayed incorrectly, and the whole notion of scientific proof. I mean, there's no such thing as scientific proof. There's no such thing as scientific fact. All there is scientific doubt minimization. We go on the hypothesis. Our hypothesis is the one that is best supported by the evidence, and that's the one that has the least doubt. It's not the one that we most believe. It's the one that we doubt the least. And we go with that. That's science. There is no proof. But that's the method, the one that has the most evidence. The simple and amongst the ones that are equally supported, we have an additional prior, which is we go amongst the one we take the one that's simplest, because our sort of implicit belief is that it's the one that's more likely. If there are two hypotheses of a phenomenon that are equally supported by the evidence and that we equally least doubt, we would tend to prefer this one. It's a prior. We tend to prefer the one that has a simpler explanation because it's somehow more likely, we believe. That's Occam's razor, at least, and Laplace, and all of these things. So the question is then, can we define a probability distribution based on this prior belief? And we can quantify this by defining a probability distribution on random programs that are prefix free, so namely halting. So for a program, for any program that halts, define its probability as 2 to the negative L, 2 to the negative length of the program. So that's the probability of a particular program. So this is in some sense a universal probability of a program. And we know that it's a probability distribution because of Kraft's inequality. So the uncountable Kraft's inequality gives us this. So this is, in some sense, like an assumed fundamental property of nature, an assumed property of the laws of physics. Like the biological world, the physical rules, the fundamental simple laws that govern our physics and the biological and physical processes of the universe are such that they can be assembled together. There's like a computer, which are the laws of physics, and then these things can be assembled together to produce programs. You know, the genetic code and then the biological processes that operate on the genetic code to produce a flower, or to produce a dog, or to produce any of you guys. That in some sense is a result of a program running, in some sense, according to this philosophy, running based on the mechanics of the processes that exist in the universe. And this gives us a prior probability, because it seems more likely that the simple ones are going to be the ones that are going to occur, the ones that are short. So what this says is that short programs under this rule are much, much more probable than long ones, exponentially more probable. But on the other hand, most sequences of length n are complex. There just aren't enough short programs to go around. That's the theorem that we proved. So short programs are more probable. Complex sequences, I mean, most sequences are complex. But any short program is likely to generates a long sequence is going to give us a highly probable long sequence. It doesn't say that there aren't any long sequences in the world. There aren't any complex objects that are big or something. It just means that if they are, they're much more likely to have been generated by short programs than long programs. So in other words, what that means is that when short programs produce long strings, they by definition produce simple long strings. So then we can use this to produce a universal probability on strings, where simple strings are more probable than complex ones of the same length. And here's the universal probability. So the universal probability of a string x is p sub u of x, which is basically summing up the probability over all programs that generate that string x of the probability of that program. And equivalently, this is the probability under this universal of b, where script b is a random program under this probability of b equals that program. So it's the probability that a random program drawn uniformly at random from the set of strings that can produce programs that are halting, produce string x. So this is essentially what this is saying. It's the probability that a random fair coin flips will create a program to print out x. Okay. Now we can think of x as natural images or natural scenes, or even the notion of sentience, our own sentience. I mean, these are things that potentially could be expressed or realized by simple programs generating large objects. And the program is what causes x to occur. Okay. So you can think of nature in some sense then as acting as a grand computer, based on the laws of physics, to ones that we know and the ones that we don't know. And then there's some random input. And if the short programs are probable, then those random inputs are going to produce outputs that have structure, just because the short programs are more probable. And like fractal images. I mean, there has been, in the past 40 years, much discussion of fractals. Right? Here's some pictures of fractals and the fractal structure of nature. I mean, everything from as mundane as like broccoli cauliflower to like the Mandelbrot set to these kinds of things, which are sort of these curves, which are sort of infinite length. On one hand, they're infinite length but finite length, like for example, the perimeter of a coastline. And there's lots of very complex objects, all of which can be generated by very, very simple programs, right? Many of which mimic nature. And these are only the programs that can be run on our computers. Right? Imagine the incredible strength of the parallel computer, but sort of is governed by the laws that govern interacting particles in physics, and what could be realized there. But I mean, so what I mean is that even though these images to us look somewhat, if anything, spectacular, they might in fact only be mundane compared to the kinds of things that could be generated by short programs. There's actually, by the way, a very short, very nice, if anyone's interested, some non-mathematical description of fractals. There's a Nova special if you're interested. Some Friday night you want something to watch. So then how do we relate this to the Kolmogorov complexity? So here's the definition of the Kolmogorov complexity. So it's very related because we're talking about halting programs that generate a string x. We might, for example, be interested in trying to compute the Kolmogorov complexity. And one way we could do this is we could, for example, try all short programs to see which of them, which is the first one to generate x. Like I think I have a program here. So, well, basically, you just keep trying longer and longer programs. So you try all bit strings up to length n, and all bit strings up to length n plus 1, and all bit strings up to length n plus 2. And we keep trying them, and if they generate, the first one that generates x and that halts would be the Kolmogorov complexity, right, of the string x. But the problem is that short programs might still take a long time to halt, or they might in fact never halt. Because how do you know if a program is going to keep running for a while and then produce the string? If you stop it early, you might have stopped it just before it halted. Or on the other hand, it might never halt. And to compute the Kolmogorov complexity, you need to sort of know, to stop, so that you can stop it because it's eventually going to halt. Because if it doesn't halt, we don't need to actually consider this program in the definition of complexity. So therefore, what we need in order to actually compute the Kolmogorov complexity is a way to tell if the program P will halt. So this next concept is the halting theorem. Have people heard of the halting theorem before? Some of you who've taken computer science classes, even undergraduate computer science classes, have seen this, but I thought that it'd be worth going through this here. So the halting theorem says that, you might say, okay, well, I just need to solve the halting problem, which basically I need to be able to have a program that takes another program and tells me whether it halts or not. And what the halting theorem says that there is no such program. There's no program H of py, which takes a program p and input y, that indicates haltingness. So h is an indicator of p halting at y, on y. And if it doesn't halt, it's 0. So to prove that this can't exist, the halting program can't exist, let's suppose that we do have such an h, a halting detector. And so we have a program that can take another program and an input and indicate by returning the value 1 if it halts, and otherwise it returns the value 0. And so given such an h, let's construct a program psi of x as follows. So what psi of x does is it takes an argument x and it runs x on itself. Okay. Well, actually, it runs h. It takes that h that it's got. It asks, what psi of x does is it takes x and it uses h to tell whether x run on itself halts or not. Okay. And then if it's the case that x on itself halts, then psi will spin forever. So basically, it takes an x and says, okay, well, if I run you on yourself, do you halt? And if so, then I'm going to go into an infinite loop. Otherwise, if I run you on yourself and I don't halt, then I'm going to return 1. So psi of x, in some sense, is an indicator of x running on itself not halting. If that makes sense. Another way of thinking about it is, psi of x, does x halt on itself? And if yes, we spin forever. Or another way of thinking about it is, if psi of x spins forever if x halts on itself, and halts if x spins forever on itself. Got it? Okay, so let's take so remember, so psi of x is an indicator of x running on itself not halting. And it's not, but if it doesn't indicate 1, it spins forever. So psi of x might, unlike h itself, which is always itself going to halt, psi might not. Psi indicates halting by not halting. So now let's construct this thing. So psi running on itself. So running psi on itself, it basically says, okay, well, that's fine. What if I'm going to run h, I'm going to run psi on itself, and if psi run on itself halts, then psi is going to run on psi is going to spin. But on the other hand, if psi run on itself doesn't halt, then psi run on itself is going to return 1. Everybody got it? So let's look at this again. So the thing is that if psi run on itself doesn't halt, then by definition, psi run on itself halts and returns 1. So that's itself a contradiction. And then secondly, if psi run on itself halts, then by definition, psi run on itself will spin forever. Again, a contradiction. So no matter what, psi itself is a contradiction. And so we base, we say that because of these contradictions, that it must be the case, that because we've led to a contradiction, that our assumption, which is that the halting program exists, must be false. So there cannot exist such a halting program. I don't know. Even though this is an undergraduate topic, I still find it interesting. So this, by the way, if you're interested, I mean, you can get more intricate. This is an instance of Gödel's incompleteness theorem, which basically, I mean, there's a very nice actual introduction to this on Wikipedia, and it basically says that any theory of arithmetic that is sufficiently rich, that there are some truths, some arithmetic truths that can't be proven within that system. And there are, other examples of contradictions, like you might have statement A. Statement A says that statement B is false, and statement B says that statement A is true. So you can't have this. This leads to a contradiction. These are very, very simple examples. Or everything I say is a lie, including what I'm saying right now. It's a self-contradiction. Right? And the halting problem is another instance of this. So the point is that because we can't detect the halting, whether or not a particular program halts, that the cohomology complexity is not computable. We can't actually compute it, unfortunately, because we can't solve the halting program. But here's where we get at this magical number omega. Suppose, on the other hand, that we could compute the cohomology complexity, and we could solve the halting program. So then, if we could, then we could actually compute this number omega. Right, so omega is just a number between 0 and 1. Right? It's basically just the following. So this number exists. Right? It's a number between 0 and 1. But we can't compute it. Right, so we know it exists, we know it's there, but it's incomputable. But what if we could compute it? What if we had it? What if we had access to omega? What would this number tell us? Well, this number would, as I said earlier, this number, if we had it, would answer any question. It's an oracle number. This number would answer any question that you could ask. Essentially, this is the halting probability. So it's the probability that a program drawn from this universal probability distribution will halt. Right? So let's say we had omega. So we can prove any n-bit specifiable theorem. Like, for example, let's say that we truncate it to n bits. Okay? And now what we do is we run all programs simultaneously, n cycles at a time. Okay? So all programs of length up to n. Like, for example, let's say here's a set of programs. We've got an enumeration, a countable number of such functions, p1, p2, and p3, and we run them. We keep running this, and we run I more cycles of pj. So eventually, all programs are going to run eventually, and eventually all programs are going to get something wrong for them. Right, so this is something that those programs that are going to halt will halt. Those programs that are not going to halt just keep running. But we've got now this thing here. We've got this number omega sub n. Once the sum of the programs, or I should say the program lengths that have halted, are such that this is true. So all of the programs that have halted so far, summing over p of 2 to the negative L of that program is greater than this n-bit truncation of omega, then it's saying that no other program of length less than n can halt. And we've therefore solved the halting problem for any program of arbitrary length up to length n. N is an arbitrary number. Okay. So how would we use this to solve a hard conjecture? Like, for example, here's a way of proving that p is equal to np, or p is not equal to np. What essentially we do is, like, let's say p is a program that searches all programs that solve some AP complete problem. Right? Like, for example, is there an Eulerian tour, or is 3-sat satisfiable? So we search over all programs in this fashion that satisfy, or that solve 3-sat. Okay. And basically what this program does is it generates all programs that satisfy it, and it halts if it finds one that's polynomial time. Okay, so it's a program that generates other programs, and it halts if it says, I found one that's polynomial time. Okay, so if halt on that program is true, then p is equal to np. So is world hunger solvable? Generate a program that generates all programs to come up with solutions, viable solutions to world hunger. And if it halts, then we know world hunger is satisfiable or solvable. So any program, any problem, any question that you might ask could be solved by this way. A program that generates other programs. I mean, this is obviously, there's practical issues associated with this, but basically, given a halting oracle, just the notion of halting, basically says, well, it eventually finds something that does what we want. that basically means it's halted, and otherwise it spins forever, it doesn't find it. It basically answers any question, any yes-no question. And from answering any yes-no question, you can answer other yes-no questions and get the solution to any problem. So it's amazing, right? So this number omega is the oracle all null, it's the omniscient number between 0 and 1.
So there must be some smallest program that's so out of all the programs that we don't know if they halt or not, there must be one that's the smallest of all of those, right?
The smallest program that halts?
The smallest program that we don't know if it halts or not. But
it's impossible to find. Because we can't solve the halting problem. Because we never know if it's going to halt. Because if we run it for 1,000,000 years or 1,000,000,000 years, maybe it's going to halt the day after 1,000,000,000 years.
So we can partition them into three categories. Ones that we know definitely halt, ones that we know definitely don't halt, and then the rest that we don't know whether they halt or not. And in those, there should be one that's the smallest of all of them.
Yeah. But that's true. But we don't know what it is. We can't find that one.
Okay.
That's all I'm saying. So while we can't compute omega, we do know something about it. We know that it's algorithmically random. That if we take the binary expansion of omega, it's basically, for all intents and purposes, random. Basically, the Kolmogorov complexity of omega itself is n minus c, greater than or equal to n minus c. So the per symbol, complexity is going to be 1 for n large enough. So basically, how do we prove this? So given omega sub n, we can solve the halting program for any program of length less than or equal to n bits, right, which we just argued. So we can describe omega n with a length, with a program of this length. Right, so it's like k of omega n bit program, because that's the Kolmogorov complexity of that number. And so what we do is let's generate a list of all programs of less than or equal to n that halt, and look at their corresponding output. So here is essentially a list of all these programs that halt. And we find the shortest string, x naught, not in this list of outputs. Okay, so x naught is not in the list of programs of length less than or equal to n that halt. Okay. And remember, we're assuming that we're given this, but all we're trying to do is look at its incompressibility. So what do we know about x naught? So the above is a program, right? It's the program, that thing of basically generating all these programs and looking at their outputs and finding the shortest string x naught, which is not in this list of outputs. That itself is a program to compute x naught, right? It has length of this, right? Because we need a program to generate omega sub n, and we need c to do the enumeration. Okay. So we can't, just by the definition, have the complexity of x naught be less than n, since we've enumerated all programs of length less than or equal to n, and we've taken x naught to be the shortest string not in that list. The shortest string not in that list, right? Because we've looked at all programs up to length n, and x naught was not in that list, and so therefore its Kolmogorov complexity cannot be less than or equal to n. So we know that this is true. And so therefore the above program must also have length less than this, because Kolmogorov complexity of x naught is the shortest such program to compute x naught. And so when we put these two things together, we get that this thing, which is the length of the program we've got, is greater than or equal to k of x of n naught, which is lower, k of x naught, which is greater than n. We get the result, which basically says that omega truncated to n bits, this is incompressible. Okay, so we're running out of time. Actually, we are out of time. I was hoping to finish this section today, but we'll finish it on Wednesday. So if you haven't read this chapter yet, then please do read the chapter. It is interesting, and it gives you an outlook. At the very least, it gives you sort of a sense of complexity theory and Occam's razor, and something that will be useful to your scientific thinking in the future. So, are there any last questions? Okay, so I will see you on Wednesday then.